All right. Hey everyone, welcome back to our series on linear algebra lectures. So today we're covering section 4.3, where we're going to take what we learned in 4.1 about eigenvalues and eigenvectors, and combine that with our new tool called the determinant of an n by n matrix. Okay, so the idea for this, and what we'll do, by the way, is we'll be just computing eigenvalues and eigenvectors of different matrices and things like that. Okay, so the idea, we'll start out with A being an n by n square matrix. Okay, and just recall what is an eigenvalue, what is an eigenvector? Well, if you have AX equals lambda x, this is our equation for eigenvalues and eigenvectors. So an eigenvector is a vector which satisfies this equation for some value lambda, which is called an eigenvalue. And the idea is if you take, so like what makes them special, if you take an eigenvector and multiply it by a matrix, what you get back is a scaled version of that vector. Well, so just to see what's going on here, if you subtract lambda x from both sides of this defining equation, and then factor out x, you'll get a minus lambda I times x equals the zero vector, right? You gotta subtract lambda x from both sides, factor out the vector x. What you're left with is a minus lambda times the identity. If you multiply that matrix times x, what you'll get is the zero vector. So in other words, x is inside the null space of this matrix. But we want to put it, I would say, a natural condition on x. We want it to not be the zero vector itself, because like the zero vector will always satisfy this equation for like any lambda. So that's not really what we're asking, right? We're asking for like non-trivial vectors that still have this property. So x has to be, what we conclude is that x has to be in the null space of this matrix. And in particular, that means that the null space can't be trivial for this matrix, which means that the matrix cannot be invertible, right? One of the characteristics of a non-invertible, of an invertible matrix is that it has a trivial null space. So for a matrix to have a non-trivial null space, it cannot be invertible, which means that its determinant must be equal to zero. And so we arrive at this equation called the characteristic equation, which is we set the determinant of a minus lambda in being the identity, the n by n identity, set that determinant equal to zero. That is the characteristic equation for a matrix. Lambda is right now a variable or an indeterminate, because right, it's the stand-in for an eigenvalue. But if you don't know the eigenvalues of your matrix, this characteristic equation is going to be a tool that helps us find them. So if you go and go a step further and actually go and compute this determinant using, cofactor expansion or whatever tools that we talked about in 4.2, what will happen is that you'll get some gnarly polynomial expression in lambda and the entries of A. That polynomial is very important, and we give it a name called the characteristic polynomial of A. Its solutions, the solutions or the roots of the characteristic polynomial, are the eigenvalues of A. And then we can go and do, compute the eigenspaces and get bases for those spaces and so on. Yeah. So let me just summarize that in a strategy. So this is going to be our eigenvalue computation strategy. I have to tell you, I really, really enjoy this particular computation. It's really fun. So the first thing we do is compute the characteristic polynomial of A. In other words, take the determinant of A minus lambda I, where lambda is treated as an indeterminate. Okay, then solve the characteristic equation for the eigenvalues lambda I. Those will be the solutions, lambda I. For each lambda I, compute the eigenspace, which is the null space of A minus lambda I. And then the last thing that we'll do is find a basis for for each eigenspace. These last two, 3 and 4, are going to be basically the same, and our final answer, when we compute the eigenspace, it's going to look something like span of v1, v2, something like this. Whatever. Okay, so and these are going to be like basis vectors. So we'll do steps 3 and 4 simultaneously. The most time-consuming part is this first bit where we have to like compute a determinant, and then I guess we there is something to be said for computing the eigenspace for each eigenvalue. That can be difficult because we don't know how many we're going to get, right? So let's just do an example. It's not bad. It goes like this. Compute the eigenvalues and corresponding eigenspaces for this matrix. So the first thing that we do is compute. I'm going to do this first example slowly so that you see what all the steps look like. So A minus lambda I is the matrix A, but then on each of the diagonal entries, subtract lambda. So minus lambda, 1, 0, 0 minus lambda, 1, 2, negative 5, 4 minus lambda. Then compute its determinant. So the determinant of A minus lambda I, we're going to have to use cofactor expansion. Not many good options. What do you think? Let's go. Let's just do cofactor expansion along the top row. I mean, that's like the definition of the determinant, but in this case, it's got a 0 up there, and it's also got a 1, so maybe it's not going to be so bad. So that's going to be negative lambda times the determinant times negative 1 squared times the determinant of negative lambda, 1, negative 5, 4 minus lambda. Then we take, we're going to add 1 times negative 1 to the 2 plus 1, which is 3, times the determinant of the 1, 2 minor of A. So 0, 1, 2, 4 minus lambda. And then, plus 0, of course. That would be from the third entry in the first row. Okay, great. So this is our determinant. We have more work to do. So this will be negative lambda times, and I'm just going to compute this 2 by 2 determinant. It'll be negative lambda times 4 minus lambda minus 1 times negative 5 plus, negative 1 cubed is negative 1 times 1 is still negative 1. So this will be minus the determinant of this other matrix, which is going to be just 0 minus 2. Right? Okay, we can keep going. So this will be negative lambda times lambda squared minus 4 lambda plus 5. Right? And then all of that plus 2. Okay, and now Okay, we don't have very many good options, but let's try something. So we're okay. So the last thing that we'll do, I'm going to. So this is a cubic polynomial in lambda. So let's just distribute that minus lambda. So negative lambda cubed plus 4 lambda squared minus 5 lambda plus 2. Um, and now we want to use some kind of strategy for computing the roots um, of this polynomial. You can use a rational roots theorem if you remember that from algebra. Um, you don't have very many options with that one, right? Because the leading coefficient here is -1 and this one is 2. And so, in fact, lambda equals 1 is a really good guess, and you can use maybe like synthetic division or something like that to check whether lambda equals 1 is a factor. Um, in fact, let's try that. Synthetic division. If you remember this from, I don't know, algebra class or something like that, good on you. In general, you can expect some easy trick for factoring these polynomials on an exam. But in reality, the problem of factoring a polynomial is just genuinely very hard. Um, and so, yeah, and so what we'll end up with at the end of our algorithm is hopefully something that we can use. Yeah, look at this. So it turns out lambda equals 1 is a factor. And our equation is going to be equal to these are going to be the coefficients of the quadratic polynomial that pops out. So this will be lambda minus 1 times negative lambda squared plus 3 lambda minus 2. We can factor a minus sign all the way to the outside. So lambda squared minus 3 lambda plus 2. And that factors as negative lambda minus 1 times lambda minus 1 times lambda minus 2. And let's just rewrite that as lambda minus 1 whole squared times lambda minus 2. Reason is we're going to talk about something called the algebraic or geometric multiplicity of an eigenvalue in just a moment. Okay, so we're going to have to get rid of some of this scratch work for the sake of space. So let's just cut out all of the in-between stuff. And we're left with lambda equals 1 and 2, right? If we set this equal to 0. If we set the characteristic, I guess that was step 2. Set the characteristic polynomial equal to 0 and solve for lambda. Well, we got lambda equals 1 and lambda equals 2. So now we need to compute the eigenspaces E1 and E2. So compute, I'm just going to write E1. This is going to be the null space of A minus 1I, A minus lambda I, right? So A minus just I. And when we do that, we have to take our original matrix and subtract 1 from each of the elements on the main diagonal. You can also take the matrix that we took the determinant of and just plug in 1 for lambda. Either way is fine. Actually, that's the way I'm going to go with. So negative 1, 1, 0, 0, negative 1, 1, 2, negative 5, 3. Now, this isn't obviously a non-invertible matrix, or it's not clear that the determinant here is automatically 0. It is because of this whole argument, but what we need is we need to compute a basis for this null space, right? So what we do is we augment, let's do it this way, put a little colon, augment this matrix with a column of zeros. So we create a homogeneous system of equations where this is the coefficient matrix and so on, and then go and row reduce. I'm going to skip this part, row reduce. The reduced row echelon form for this matrix is going to be, it's not bad, right? We can probably interchange, we don't even have to interchange. If we just multiply row 1 by -1, then add -2 row 1 to row 3. Then if we pivot around this next entry, we'll clear out the second row, and you may have to clear out this 1 as well. But that's the entire row reduction. After you finish that, it will be in reduced row echelon form. So it's an easy row reduction, but I'm still not going to do it because anyway, that is a good exercise for you to try on your own if you're still uncomfortable with row reduction. Our final matrix will look like this. Okay. Notice we got a row of all zeros. That was guaranteed to happen, but you should think about why it was guaranteed to happen. We also have a free variable, which was totally necessary, right? So x3, I'll just call it, is free. The third variable in this homogeneous system. So we'll set t equal to x3. Then by this equation, we have x1 equals t and x2 equals t, right? It's like x1 minus x3 equals 0. Okay, well then x1 equals x3. And x2 minus x3 equals 0. Well, then x2 equals x3. And x3 is already equal to x3. So we'll just put it like this. So E1 is the span of the set of vectors that look like t, t, t. It's not the span, it's this. It is this set of vectors. It's the set of vectors that look like t, t, t. And that set, or that whatever that subspace is, has a basis of a single vector called 1, 1, 1. Or 2, 2, 2, or 10, 10, 10, it doesn't matter. We're looking at the span. So this is a basis vector for the eigenspace. And so this is what your final answer will look like. Okay, let's try E2. E2. So this is going to be the null space of A minus 2I. I'm just going to write down what that matrix is, right? Augmented matrix for the homogeneous linear system. So that'll be -2, 1, 0. 0, -2, 1, 2, -5, 2. Again, it's not obvious that this is a dependent, non-invertible matrix, but it is. And when we row reduce, it will look like 1, 0, -1/4, 0, 1, -1/2, 0, 0, 0. Okay, and so once again, we have a free variable, which we were expecting. This tells us that x1 is positive 1/4 x3. I haven't defined the parameter yet, so this looks a little bit different from what I just wrote. We'll define a parameter in just a second, though. So x1 is 1/4 x3. x2 is 1/2 of x3. And x3 is just x3, which is free. So E2, well, before I do that, let's do our parameter. So set, you want to do t again, t equals x3, so that E2 is the set of vectors of the form 1/4 t, 1/2 t, t, which is the span of just one vector in the basis again, 1/4, 1/2, 1. By the way, if you really like it, like I do, I don't like having fractions in my basis vector. Sometimes you need to have fractions in your basis vector, but if it's just a random basis that we're asking for, we might as well scale these things up. So this is the same as the span of 1 to 4, right? If I just multiply that basis vector by 4, I get another vector in the eigenspace, but the eigenspace is one-dimensional. So any non-zero vector inside of the eigenspace is a basis vector, or taken by itself forms a basis of that eigenspace. So I might as well take this one because it's prettier to look at. But yeah, this is final answer. Okay, so it wasn't so bad. The computation is lengthy, but not terrible. So before we do another example, I want to point something out. Notice something interesting happened. Lambda equals 1 showed up as a root of the characteristic polynomial, but it was a double root. If you were to graph this polynomial, y equals determinant of a minus lambda I, it would have had a graph that looks like this. Something, something, something comes down, bounces off lambda equals 1, and then passes through lambda equals 2. Something like this. If you remember from algebra, where all this polynomial discussion was, we gave a name to an x value, or in this case, a lambda value, for which the root, for which that x value being a root of the polynomial was actually a double root. It was called it was called multiplicity. It was a multiple root or whatever, but specifically an algebraic multiplicity. So algebraic multiplicity is multiplicity of root of the characteristic polynomial. Okay. The geometric multiplicity is something different. So every eigenvalue shows up, has a corresponding eigenspace. It's a space of eigenvectors that all, when you multiply those vectors by, or multiply A by those vectors, you get a scaled version of that vector back, and the scale factor is the eigenvalue, right? That's what the eigenspace contains, a bunch of eigenvectors of that form. However, that eigenspace is a subspace, and that subspace has a dimension. The dimension of that subspace, we're going to call it the geometric multiplicity. We don't need to call it multiplicity so much. We will, because that's the trade. This is the industry standard. But I want to place emphasis on the geometry part, right? What we're saying is that there's an entire line that gets preserved under the matrix transformation defined by A. In fact, there are two lines. One of them, each one is one-dimensional, and the number one, the dimension of that subspace, tells us how much is being preserved by that particular how much of the whole space is being preserved by that linear transformation. So the geometric multiplicity we're taking as dimension of the eigenspace. Okay, these seem totally arbitrary right now. It's like, great, you've given us two definitions of multiplicity and we don't know what either of them means. I know. We'll see very, very soon that the distinction matters dramatically, because we're going to come up with a cool strategy for solving some different types of problems using eigen values and eigenvectors, but it's only going to work when these multiplicities match. So the previous example, they didn't match. Notice for lambda equals 1, it had algebraic multiplicity 2, but geometric multiplicity 1. Now we're going to do an example where the multiplicities all line up. So let's do it. Look at this beautiful matrix. It's well, it's not quite symmetric, but it's definitely got a lot of linear dependence in the rows. So, but we're going to same thing, compute the eigenvalues and corresponding eigenspaces for this gnarly matrix. Okay, so let's just skip right to the determinant of A minus lambda I, which is going to be the determinant of 1 minus lambda, 0, negative 1, 2, negative lambda, negative 2, negative 1, 0, 1 minus lambda. May I suggest cofactor expansion along the middle column? So this is going to be negative lambda times the determinant of negative lambda times, okay, I'll write it, times negative 1 to the fourth, right, to the 2 plus 2, because this is the 2, we're going to compute the 2, 2 cofactor. So that'll be times the determinant of 1 minus lambda, 1 minus lambda, negative 1, negative 1. Okay, so now we just have to keep track of minus signs. This is negative lambda times, this determinant is 1 minus lambda squared minus negative 1 times negative 1, which is 1. Okay, that's not so bad. 1 minus lambda squared is lambda squared minus 2 lambda plus 1. But then we subtract 1, so the constant terms will cancel. We have minus lambda times what survives, lambda squared minus 2 lambda. And so our final factored form for this answer is negative lambda squared. Like, we can factor another lambda out of here, right? And what survives is times lambda minus 2. When we set that equal to 0, we get that lambda is equal to either 0 with algebraic multiplicity 2, or lambda equals 2 with algebraic multiplicity 1. Okay? And now let's compute E0. Let's compute E2 first, just because that seems to be the case that's more similar to the previous ones that we saw. So this is going to be the null space. Well, I'll just write down the augmented matrix. So lambda equals 2, we have negative 1, 0, negative 1, 2, negative 2, negative 2, negative 1, 0, negative 1. Row reduction in this case is super easy. We have negative 1, positive 1, 0, positive 1. 0, well, I'll just do it in 2 steps. -2, -4, 0, 0, 0. I guess this is just going to be 1, 2. Yeah. Okay. And so now we have x1 equals -x3, x2 equals -2x3, and x3 equals just x3, which is 3. If t equals x3 is our parameter, then E2 is the subspace of vectors of the form -1, -2, 1. Oh, sorry. Haha. T is the parameter. So -t, -2t, t. That's the subspace itself, parameterized by this value t. But now we have to like go and write it as a basis, or find a basis. So write it as the span of one basis vector. So span -1, -1, -2, 1, like this. Okay. Some people, just like we were clearing denominators, like to have the leading value equal to 1, in which case you could, multiply through by a -1, and it would be like 1, 2, -1. You're welcome to do that on an exam if you like how that looks better. I prefer the method of minimal effort. So, yeah, okay. Great, now let's compute E0. So this will be interesting. Our matrix is going to look like -1, 0, -1. Okay, A minus 0i is just A. So it's 2, 0, -2, wait, did I get this wrong? +1, +1. And then -1, 0, 1, like this. Oh, augment with 0, of course. Well, this thing, you can row reduce it just by squinting at it. You just pivot around this 1 and we're literally done. So, yeah, okay. So 1, 0, -1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Excellent. What do we do with this system? Okay. x1 is x3. Sorry, x1 minus x3 equals 0. So x1 equals x3. But then we have 2 rows of zeros, which means that x2 and x3 are both free. So x2 equals x2 is free. And x3 equals x3 is also free. So in other words, the null space here is 2-dimensional. How do we parameterize it? If you remember, it's we would just let s equal x2 and t equal x3. Then E0 is the set of vectors of the form T S T, right? The first and last entries have to match. The middle entry can be anything. Notice, just take that, take that thing and then multiply it by A. You'll get a column vector of the form t minus t, 2t minus 2t, and -t plus t. That's 0, 0, 0. And TST could be like S. It literally didn't matter what S was. Could have been any number, and you still would get 0, 0, 0, right? And notice we're not okay, these eigenvectors, 0, 0, 0 is inside this eigenspace, but it's not an eigenvector. But notice there's two whole dimensions of non-zero eigenvectors living inside of this eigenspace. So this is a very big space. It's a whole plane. Um, and so we'll just write it as a span. So what is the span here? Well, we need to break it up as like, oh, okay, let's do it this way. Without writing a span, I can write this as a sum. So it's the set of vectors of the form t0t plus 0s0. And if you want to write that as linear combinations, this is going to be t times the vector 1, 0, 1 plus s times the vector 0, 1, 0. By definition, that's literally, since s and t are free real variables, this is literally the set of linear combinations of 1, 0, 1 and 0, 1, 0. So we'll take those to be our basis vectors and be done. So this is the span of 1, 0, 1 and 0, 1, 0. That's it. That's pretty impressive. Notice geometric multiplicity 2. So algebraic multiplicity is 2. Geometric multiplicity is also 2. Same here, algebraic multiplicity was 1, and the geometric multiplicity was also 1. Because it was, the E2 eigenspace was just a line, whereas the E0 eigenspace was an entire plane. Great. Okay, so so this is a gnarly computation. Sometimes there are ways to speed it up, so let's talk about those real quick. So we have a nice theorem which we are going to prove by inspection. The eigenvalues of a triangular matrix are going to be the entries on the main diagonal. How do I know? Because theorem 4.2 tells us that the determinant of a triangular matrix is the product of its main diagonal. So, so if you do a minus lambda I, where a is triangular, this is going to be the determinant of star minus lambda, and some other stuff, and then zeros on top, something like this. Which actually we can name these stars. I can tell you exactly what they are. They're A11, A22, all the way up to ANN. Well, by theorem 4.2, the determinant of this matrix is literally A11 minus lambda times all the way up to ANN minus lambda. You want to set that equal to 0? Then what are the roots? It's just lambda equals AII, the diagonal entries. So the eigenvalues of a triangular matrix are just the diagonal entries. You can just read them off of the diagonal. Unfortunately, row reduction does change the eigenvalues of a matrix. So if you do row operations, you do not preserve the eigenvalues. So it's not like we can just, oh, well, in that case, let me just put it in row echelon form and then take the determinant and I'm done. No, unfortunately, that is not how it goes. So instead, we're going to have to come up with a different way to reduce matrices that is compatible with eigenvalues and eigenvectors. That will be the content of the next video, section 4.4. But for now, we have one more characterization of invertible matrices. So this will be added to the fundamental theorem of invertible matrices. I won't write it all out in this video, but you can add this to the list, right? In the last video, we saw that a matrix is invertible if and only if its determinant is non-zero. Well, here we're going to say that a square matrix is invertible if and only if 0 is not one of its eigenvalues. Well, how do we go about proving that? Take the determinant of A. Okay, well, the determinant of A is precisely the determinant of A minus 0I. Now, if this is equal to 0, then 0 was an eigenvalue of A. Now we just have to think hard about this with a bit of logic. Okay. So if the determinant of A, which is also the determinant of A minus 0I, if that's equal to 0, then 0 is an eigenvalue of A. But that means the determinant of A was equal to 0, so A was not invertible. In other words, if A is invertible, then this determinant cannot be equal to 0. But that's what the theorem says. So, a square matrix is invertible if and only if 0 is not one of its eigenvalues. It's a nice exercise in logic. It's kind of cool. Right. Okay, so the last thing that we'll do is we'll explore an application of eigenvalues. Oh, this is not the last thing. This is almost the last thing. This is going to set the stage for section 4.4. So we have the following theorem. Okay, start with A is a square matrix. X is an eigenvalue of A. Sorry, X is an eigenvector of A with corresponding eigenvalue lambda. Okay, then for any positive integer n, so n is greater than or equal to 1 and is a whole number, then a to the n times x will be lambda to the n times x. In other words, x is still an eigenvector of a to the n, but the eigenvalue is now lambda to the n. Interesting. Okay, and then if a is invertible, we also have that x is an eigenvalue of the inverse of a. And the corresponding eigenvalue again. X is still an eigenvector of the inverse, and the corresponding eigenvalue is 1 over lambda. So the multiplicative inverse of lambda. If you put those two together and we still have an invertible matrix A, then what we can say property 1, but instead of just positive integers, it's literally any integer. X is still an eigenvector of A to the n, with eigenvalue lambda to the n, even if n is like a negative number, negative whole number. Yeah, you just do lambda to the, or a to the -5 is like a inverse to the 5th, or a to the 5th inverse, or something like that. Either way, and right, and that goes back to our discussion about matrix powers. So, okay. So, in light of that theorem, let's go and compute this matrix 0, 1, 2, or 0, 2, 1, 1 to the 12th times 5, 1. So this is going to be crazy. Now, instead of going and just really computing this, I don't feel like raising a 2 by 2 matrix to the 12th. We have to multiply it by itself, hope for a pattern. There won't be one, and so we just have to, it would be like a crazy amount of matrix multiplication. I would prefer a different strategy. So let's go this time instead and compute some eigenvalues and eigenvectors, just so that we can hope to apply the previous theorem. So a minus lambda I, determinant, so characteristic polynomial of A, is the determinant of negative lambda 1, 2, 1 minus lambda, which is negative lambda times 1 minus lambda minus 2, which is lambda squared minus lambda minus 2. Okay, I'll write that. Lambda squared minus lambda minus 2, which factors as lambda minus 2, lambda plus 1. Set that equal to 0, and we have lambda is equal to 2 or -1. Not so bad. 2 eigenvalues. Let's compute the eigenspaces while we're at it. This is not so bad. So E2 is the one where we have the null space of -2, 1, 2, -1. Create the augmented matrix, row reduce. Notice the second row is a carbon copy, is a negative of the first row. So -2x1 equals, plus x2 equals 0. So x1 equals 1/2 x2, and x2 equals x2 is free. So the eigenspace E2 is going to be the span of 1/2 1. And because of simplicity, I'm going to make that 1, 2. Multiply it by 2 so that we're looking at something nice. Just so that we can verify real quick, multiplying this vector, this basis vector, by A should give something that's twice as big. So 1, 2 times the original matrix A, this guy, is going to be 2, 4, which is twice as big, right? So this is an honest eigen vector with corresponding eigenvalue 2. And since it's not 0, it makes up a basis for the eigenspace E2, so we can stop there. How about for E -1? That'll be the null space of -1, 1, -1, 1, 2, 2, 2. Sorry, +1. A minus lambda I, but lambda is -1, so it'll be A plus I. So 1, 1, 2, 2. There we go. Notice the second row is just double the first. So x1 equals -x2. x2 is again free. So E -1 is going to be the span of -1, 1. And let's just check again to make sure that all this does is 1, -1. No, -1, 1, while they're the same. Let's check to make sure that this does indeed flip the sign of our eigenvector. So -1, 1 times dot product with 0, 1 is going to give you +1, and dot product with 2, 1 will give you -1. So we get, when we multiply A by this vector, -1, 1, we get 1, -1 as the output, which is the negative of this vector. So we did it right. Okay. This is a mind bender without writing anything down anyway. Okay, so now what is the use of this? Notice that these vectors are linearly independent. I'm talking about these two. These two vectors are linearly independent. That's kind of powerful. That tells us that this vector 5, 1 that we're trying to compute, we'll call it x. This tells us that x equals c1 times 1, 2 plus c2 times -1, 1. In other words, x is a linear combination of eigenvectors. That's kind of powerful. And okay, I'm not gonna. You can work this out. It's worked out in the book, but you know how to find linear combinations, right? Set up an augmented system, row reduce. You'll extract the coefficients, and then we write them for C1 and C2. As it turns out, C1 is equal to 3. I hope. Now C1 is equal to 2, and C2 is equal to 3. Let's just double check that. We want to get 5, 1 I think it's -3. I think it'll be -3. So -3 times -1 is 3, plus 2 is 5, and -3 times 1 is -3, plus 4 is 1. Okay. Uh, you should probably double check. And in practice, you'll have to actually set up a linear system and solve it. But in a 2x2 case, you can pretty much do it in your head. So like this. But also the book has an answer. So, okay. So knowing that, this tells us that a to the 12th times x is a to the 12th times, is 2a to the 12th times 1, 2 minus 3a to the 12th times -1, 1. And now, these are both eigenvectors. 1, 2, and -1, 1 are eigenvectors of A. Let me move my lingering question down, and then we'll come back to it. By theorem 418, I don't need to know a to the 12th in order to compute a to the 12th times an eigenvector. I just do lambda to the 12th times that eigenvector. So this is, by theorem 418, 2 times lambda to the 12th. We have to do the correct lambda. So 2 to the 12th times 1, 2 minus 3 times -1 to the 12th times -1, 1. Okay. 2 times 2 to the 12th is 2 to the 13th, which is 8192. No. 1024 is 2 to the 10th, so 2048, 4096 is the 12th. And so to the 13th, yeah. This is 8192. This is 8192. 2 to the 13th, really? Okay, and then we have to do one more power. So I think this is 16,384. Yeah, I'm convinced. Okay. This is what you get for doing arithmetic on the fly. The next one is much easier. So minus -1 to the 12th. I got this. It's 1 times -3. Oh, okay. Times 3 is like 3. We can, okay, we'll put a -3 and +3. I'm just going to change that. I'm just going to distribute the minus. Okay. So final answer is 8195 and 16,381. Final answer. And okay, we did a whole eigenvalue, eigenvector, eigenspace computation, and then solved a linear system, and then had to do some gnarly arithmetic, and it was still less work than trying to take a to the 12th. You imagine sitting here multiplying matrices 12 times. You would get there more slowly than we got here with this strategy, right? Now imagine, now we just say, okay, what if the strategy worked in the 3x3 situation? Like if A was a 3x3 matrix and you still had to raise it to the 12th. Or, God forbid, what if we had to raise it to the 112th power? Okay, now suddenly matrix multiplication just simply is not an option, right? It's not worth it. I would rather take 0 points on the exam or something, right? We have to reach a point where uh, the computation isn't worth it. However, uh, powers of matrices, if you may or may not have read section 3.7, but in general, powers of matrices are uh, they're like one of the main applications of matrix theory. Just being able to iterate a matrix multiple times. The more that's how most simulations are conducted, are by just iterating powers of a matrix. So yeah, this is this is gonna come up in life like all the time. So, but if it's more than a 2 by 2 matrix, we seem to be doomed unless we can do this computation. So the question is, does this strategy generalize? And if so, like when and how, right? How does it work in higher dimensions? Um, Let me tell you the answer. The answer is theorem 419. Okay? And it goes like this. Suppose A is an n by n matrix with eigenvectors v1 all the way up through vm with corresponding eigenvalues lambda 1 up through lambda m. Okay, then if x, which is a vector in Rn, if x can be written as a linear combination of those eigenvectors, then our strategy works for any integer k. If you want k to be negative, you also have to impose the requirement that a is invertible. But for any, okay, whatever, for any integer k, you want to compute a to the k times x. Well, then you could do a to the, lambda to the k, lambda I to the k times vi times ci, and then add up all those things. In other words, do what we did, right? Write x as a linear combination of eigenvectors, and then instead of doing a to the k times those eigenvectors, do lambda to the k times those eigenvectors, and then add it all together when you're done. That's pretty good. However, I have to caution you. This is a pretty strong if. In fact, we will encounter many situations where it just simply is not possible to write x as a linear combination of eigenvectors. And we're going to have to just deal with it. It's very sad. But in other words, when we're exploring this theory of eigenvectors and eigenvectors, it pushes back, right? It's like that says, okay, yes, you can do this, but only sometimes. So that's what this caution is. It only works when x is inside of the span of your eigenvectors or span of your eigenspaces, right? And so but in the direction of trying to understand when this will work and how, we do have one theorem that we're going to state without proof. Actually, I don't think we've proved anything this lecture, which is very sad, but you know how it is. No, we did. Okay, anyway. So if lambda 1 through lambda m are distinct eigenvalues, so if all of the eigenvalues in the corresponding, breakdown are distinct, then we do get we get guaranteed that the corresponding eigenvectors, will be linearly independent. It's not like they're going to be linearly dependent. Okay, and the proof of this is intense, but not impossible. It's highly geometric. Okay, so distinct eigenvalues correspond to linearly independent eigenvectors, right? And so if you have n distinct eigenvalues, if you have n distinct, like different eigenvalues, then you can get theorem 419 for any vector. You can do our computation for any vector in Rn. That's the consequence, right? You get, that is a very strong if. You need your characteristic polynomial to factor perfectly with no duplicate roots, and all of them have to be real roots. That is uncommon. Like, you have to kind of cheat in order to get a matrix that does that. And so, but the situation is not that dire. There is, so what we'll talk about next time is strategies that kind of, the situation is not this bad. It'll get slightly better. We'll find more cases where we can do more things, even if we're still a little bit restricted. And then we'll talk about those in section 4.4, similarity and diagonalization. And I will see you in the next video.